So substituting the value of qx, we have negative k. Let me change the position of dy and dz. So we have dy dz partial derivative of t with respect to x is equal to this part here, this term. Right? So we have negative k dy dz partial derivative of t with respect to x minus partial derivative of the function. You have k dt dx dy dz with respect to x. Okay. So considering only these two, we can notice that we have some similar terms right here. Okay. And if we gonna move all our expressions on the left side, we can see that we can cancel out this term because this now will become a positive, then this also will become positive, yan, right? So we can cancel this out because the terms are similar but they have an opposite, different sign. The one is negative and the one is positive. So when you add these two, then they are 0. Okay. So if we're gonna have this, if we will gonna have this expression, so if we will move our q leaving in this side, q leaving the system in this side, then we can only have, or this expression will remain, right? Because we can cancel out these two parts here. Okay, so having this expression, the q leaving, the q entering minus the q leaving, or the delta q, is that we can only have these remaining expressions. Therefore, we have k dt dx dy dz. Okay, so this is for entering minus leaving, and right. Okay, so having this concept, or having these mathematical expressions, now we can also do the same for y and z, right? Okay. Okay, where are we? Okay, right? So let me copy again this part. Okay. Okay. So again, if we will gonna use this expression that the what do you call this, the qx minus, the entering q minus the leaving q is equal only to this expression. Okay, so having these expressions, we can now simplify this energy balance by having our q x minus this part here x plus dx. Okay, and then plus dy, y minus q, y plus dy, plus the z part, the q of z, then minus z plus dz, right? And then after this whole uh, uh, heat going in and out of the system, can now add this uh, G or heat gen, which is equal to this part. So we have heat gen equal to only this part, the stored energy. Okay, and this expression is equal to this expression, right? This expression, this part, is equal to this part. So we have, let's copy this. Ay, sorry. Yan. Yan. Okay. Okay. So doing the same thing, we can now have the same principle on this part. Okay. The y direction. So we have d over dy, k, dt, dy, opo, dx, dy, dz. Okay? And then plus uh, this term. So we have uh, using also the same principle. So we have d partial derivative of z because we are now talking about the x direction. Okay, so and then we have k partial derivative of the temperature with respect to z, dx, dy, dz. Okay, and then plus this part, which is the heat generation. So we have g, dx, dy, dz, then equal to energy stored. Yan. So we've almost done. We've only left with the last term. Okay? Okay. So recall that we can also express this energy stored in terms of our what do you call this? The formula m of course the totality or the summation of m c delta t, right? Delta t. Okay, you remember this expression. But since we're dealing with some uh, time basis, so we need some we need to express this in certain time. Okay, so we now have the rate. Okay, so expressing this, we have mc, and if we take the, of course we are talking about the derivative here, so we need to take the partial derivative of the temperature with respect to time, right? Okay, because we are now in the rate basis. Okay. So having this expression mc delta t, and also recall that our density is equal to what again? Mass over volume, right? And our volume here is that once again, say this is our element. Our volume is what? The product of this dx, dy, and dz, right? So therefore, if we gonna substitute the volume using our element, then we have dx, dy, dz. You know, the product of this dx, dy, and dz to take the volume of this element, right? Then, since we have now this expression, we can now easily solve for the value of our m. M is equal to, can move this, we have density dx dy dz, right? Okay, so we can now substitute our value of m here. So our m is density dx dy dz, and then our c, then the partial derivative of t with respect to time. Okay, so now this will complete our equation, and we will gonna substitute this whole term in this part. Okay, and doing that, we now have, let me copy na lang, we now have let's delete this, then substitute this energy stored. Okay, so we have the density dx dy dz, oops, c dt over dt. Okay, okay, what did you notice? Okay, so as you can see, all the terms have this expression dx dy dc, dx dy dc, dx dy dc, all of them, right? So we can easily cancel this out to simplify our equation. Oops. Okay, so doing that, we now have the this term plus the exactly the same term but in terms of y, plus our generation, and then this energy stored, and I mean rho c dt dt, right? Okay, so that's it. The general general expression or derivation of heat conduction in rectangular coordinate system. Okay, so on other expressions is that they divide uh, uh, the whole term by k, so that we can also express this like this like this. Plus, right, because we divide the whole term with k, and also this part here, right? So we can also use this expression. So that's all.